When we last met, we were drawing Lewis structures to represent molecules. This is a good first step in visualizing a molecule, but Lewis structures are two-dimensional. Today, we want to go a step further and take a three-dimensional look at molecules.
In this lesson, you will predict the shape of a molecule based on the electron dot diagram, explain what determines molecular polarity, and describe intermolecular forces.
So, let's start by talking about why molecular geometry would be important in the first place. Our job in chemistry is to study matter. We have talked about the properties of elements and how we can predict them based on the element's location on the periodic table. We want to be able to predict the properties of molecules as well. This will get us one step closer to understanding chemical reactions. The type of bond involved plays a part in the properties of molecules, but so does the shape of the molecule. How do we determine the shape of a molecule?
Let's start with something simple, like a hydrogen molecule. You will recall that a hydrogen molecule consists of two hydrogen atoms with a shared pair of electrons between them. You can see that the shape of this molecule would be linear. What about a molecule of HCl? Again, you can see that the shape of this molecule would have to be linear. In fact, any molecule that contains only two atoms is going to be linear.
The student is going to build a model to represent a molecule of HCl. The model she builds shows how a molecule containing only two atoms is linear.
It gets a bit more complicated when molecules contain more than two atoms. In order to predict the geometries of these more complicated molecules, we need to understand VSEPR theory. VSEPR stands for valence shell electron pair repulsion.
Valence shell electron pair repulsion. The VSEPR theory basically says that since electron pairs will repel each other, the pairs of electrons surrounding the central atom in a molecule will be as far apart from one another as possible.
First, we're going to consider molecules in which the central atom has no unshared pairs of electrons. Let's look at carbon dioxide. First of all, we need to draw the Lewis structure for carbon dioxide. We did this one in our last program. The carbon atom is the central atom, and it is bonded to each oxygen atom with a double bond. The distance between the oxygen atoms will be the greatest if they lie on opposite sides of the carbon atom. This will make them 180 degrees apart.
The student is building a model to represent the carbon dioxide molecule. She will use springs to represent the shared pairs of electrons in the double bonds. From the model, you can see that the atoms in the carbon dioxide molecule form a linear geometry.
Whenever two atoms are bonded to the central atom and there are no unshared pairs of electrons on the central atom, the molecule will have a linear shape. This will result in a 180-degree angle between the atoms.
Now, let's try CH2O. We also did the Lewis structure for this one in our last program. In this one, the central atom, carbon, is surrounded by three other atoms. These three atoms will achieve VSEPR by forming the corners of an equilateral triangle. This will make them 120 degrees apart.
The student is building a model to represent CH2O. Again, she will use springs to represent the shared pairs in a double bond, and she will use sticks to represent the shared pair in a single bond. You can see how the atoms form a triangle.
Whenever three atoms are bonded to the central atom and there are no unshared pairs of electrons on the central atom, the molecule will have a triangular shape. Because the three atoms all lie in the same plane, this shape is called trigonal planar. This will result in a 120-degree angle between the atoms.
Another example without any unshared pairs on the central atom is CH2Cl2, which we did the Lewis structure for in the last program. In this one, the central atom is bonded to 4 other atoms. In order for the atoms to achieve VSEPR, they will form a tetrahedron. In a tetrahedron, the angle between the atoms is 109.5 degrees.
The student is going to build a model to represent CH2Cl2. The black ball represents the carbon atom in the center. The 2 yellow balls represent the 2 hydrogen atoms, and the 2 green balls represent the 2 chlorine atoms. You can see that the atoms are spread evenly around the central atom, forming a tetrahedron.
Whenever 4 atoms are bonded to the central atom and there are no unshared pairs of electrons on the central atom, the molecule will have a tetrahedral shape. This will result in a 109.5 degree angle between the atoms.
Now, let's try water, H2O. Oxygen has 6 valence electrons, and each of the hydrogen atoms has 1, for a total of 8 valence electrons to work with. So, we put oxygen in the middle, bonded to each hydrogen atom, with 2 unshared pairs of electrons as well. We might think that this molecule will be linear, because it only involves 3 atoms. However, VSEPR takes all of the electron pairs into account, not just the shared ones. Let's think of it this way. There are 4 electron clouds surrounding the oxygen atom. 2 of the clouds are shared pairs, and 2 of the clouds are unshared pairs. 4 electron clouds make this more similar to a tetrahedron than a linear molecule. But remember, 2 of our clouds are unshared pairs. This makes a bent shape.
The student is building a model to represent H2O. The model kit design prevents the student from thinking that this would be a linear molecule, which would be a big mistake. Taking the unshared pairs of electrons into account, the model kit provides the student with a look at this bent molecule.
Whenever 2 atoms are bonded to the central atom and there are 2 unshared pairs of electrons on the central atom, the molecule will have a bent shape.
The last one we are going to try is NH3, another Lewis structure we drew from the last program. At first glance, you may think that this is going to form a planar triangle, just like CH2O. But you have to consider the unshared pair of electrons on the nitrogen atom.
Again, this is more similar to a tetrahedron because it has 4 total electron clouds. We know that one of the clouds is an unshared pair of electrons. And we get a molecule that is indeed triangular, but the atoms are not all in the same plane. This model is called trigonal pyramidal.
The student is going to build a model to represent NH3. Again, the model kit is designed to prevent the student from making the mistake that this would be trigonal planar. Taking the unshared pair of electrons into account, the model kit provides the student with a look at this trigonal pyramidal molecule.
Whenever 3 atoms are bonded to the central atom and there is 1 unshared pair of electrons on the central atom, the molecule will have a triangular shape. The atoms will not lie in the same plane. Instead, they will form a sort of pyramid, so this shape is given the name trigonal pyramidal.
Now, it's your turn. Your local teacher is going to put the following assignment on the board for you. For each of the molecules listed, you are going to draw the Lewis structure, tell how many atoms and unshared pairs of electrons surround the central atom, and predict the shape of the molecule. Then, you are going to construct a model of the molecule. This is an important step because it will help you be able to visualize these molecules. You will either be using a model kit or toothpicks and gumdrops to make your models. When you have completed this, your local teacher will check your models and help you with any that you have missed.
Local teachers, please pause the tape now and give students time to work lab activity.
I hope you enjoyed building your molecular models. Now, let's try something a little bit tricky just for fun. Let's see if we can determine the molecular shape for C2H4. First of all, we have to draw the Lewis structure. We'll start by adding up the total number of valence electrons. Each carbon atom has 4, and each hydrogen atom has 1, so that gives us a total of 12. Next, we'll put the 2 carbon atoms in the middle, with 2 hydrogen atoms bonded to each one. But our carbon atoms still don't have enough electrons to be happy or stable, so we give each one a lone pair of electrons. Now we count 2, 4, 6, 8, 10, 12, 14. That's not going to work. Instead, we will try a double bond between the 2 carbon atoms. That gives us 2, 4, 6, 8, 10, 12. Perfect. Now that we have the correct Lewis structure, we can go about the business of determining shape. The tricky part is that we actually have to determine the shape for each carbon atom. They are each bonded to 3 other atoms with no unshared pairs, so that makes them trigonal planar. So, 2 trigonal planar shapes connected by a double bond. That wasn't so hard.
The student is building a model to represent C2H4. He will again use springs to represent the double bond between the 2 carbon atoms. This gives a molecule consisting of 2 planar triangles attached with a double bond. Now we're going to use our knowledge of molecular geometry to determine if molecules are polar or nonpolar. You will remember that we have already discussed how to determine if a bond is polar. We are going to combine that knowledge with molecular geometry to explain polarity in molecules.
You will recall that a bond is considered polar if the electronegativity difference is between 0.3 and 1.7. You will also recall that a polar bond has a positive end and a negative end. Well, so does a polar molecule. In order for a molecule to be considered polar, it has to contain polar bonds that are positioned in such a way as to create a positive end and a negative end to the molecule. Let's look at a water molecule. The bond between each hydrogen atom and the oxygen atom is polar because the electronegativity difference is 1.4. This puts a partial positive charge on the hydrogen atoms and a partial negative charge on the oxygen atom. According to VSEPR, a water molecule will be bent. This molecule will be polar because we can split it into a partially positive end and a partially negative end.
A molecule is considered polar if it meets 2 criteria. The bonds in the molecule must be polar, which means that the difference in the electronegativities must be between 0.3 and 1.7, and the atoms must be oriented in such a way as to give the molecule a partially positive end and a partially negative end.
Now, let's look at an example that meets one, but not both of these requirements. Carbon tetrachloride, or CCl4. When you built your molecular models, you determined that carbon tetrachloride would have a tetrahedral shape with a carbon atom in the middle. This means that the molecule contains 4 bonds between the carbon atom and a chlorine atom. The electronegativity difference between these 2 atoms is 0.5, so the bonds are polar with the partial negative charge on the chlorine atoms and the partial positive charge on the carbon atom. If you look at carbon tetrachloride, you see that the negative charges surround the positive charge. There is no way to divide this molecule into a positive half and a negative half. So, even though it contains polar bonds, the molecule is nonpolar. Of course, molecules are also nonpolar if they contain only nonpolar bonds.
A molecule is considered nonpolar if it contains only nonpolar bonds. A molecule also is considered nonpolar if it contains polar bonds that are distributed in such a way that the molecule does not have a positive and negative end.
You will need your lab sheet from your model building, as well as a chart of electronegativities for your next activity. Your local teacher will pause the tape while you look at each of the molecules you built earlier and do two things. First, determine if the bonds in the molecule are polar or nonpolar. If the bonds are polar, label the end with the most electronegative element, partially negative, and the other end, partially positive. Then, determine if the overall molecule is polar or nonpolar. When you have completed this task, I'll be back to go over this with you.
Local teachers, please pause the tape now and give students time to work part 2 of lab activity.
So, let's see how you did. First, you had HI. The difference in electronegativities is 0.4, so the bond is polar with a partial positive charge on hydrogen and a partial negative charge on iodine. Since there are only 2 atoms involved, it is easy to see that this can be divided into a positive end and a negative end. So HI is a polar molecule.
CBr4 doesn't have any polar bonds, so the molecule can't be polar. CBr4 is a nonpolar molecule.
H2S has polar bonds and a bent shape. This allows for a positive and negative end. Thus, H2S is a polar molecule. HCN has carbon as the central atom. Both the hydrogen-carbon bond and the carbon-nitrogen bond would be polar. In the hydrogen-carbon bond, the hydrogen would get the partial positive charge. In the carbon-nitrogen bond, the carbon would get the positive charge. This puts enough positive charge on one end and negative charge on the other end. So, HCN is a polar molecule. Of course, you realize that we had already done CCl4. SF2 has polar bonds and a bent shape just like H2S. It is also a polar molecule. PCl3 has polar bonds and a trigonal pyramidal shape. This allows for a division between the positive ends of the bonds and the negative ends of the bonds. So, PCl3 is a polar molecule. CH3Cl has polar bonds and a tetrahedral shape. In the carbon-hydrogen bonds, the hydrogen atoms have the partially positive charge. In the carbon-chlorine bond, the carbon atom has the partially positive charge, and the chlorine atom has the partially negative charge. This gives a positive and negative end to this molecule, so CH3Cl is a polar molecule. CH2S has polar bonds between the carbon and each hydrogen, but nonpolar bonds between the carbon and sulfur. This puts a partially positive charge on the 2 hydrogen atoms and a partially negative charge on the carbon atom. The shape is trigonal planar. This molecule can be split into a positive end and a negative end, making CH2S a polar molecule. SCl2 is just like SF2. It is a polar molecule.
This knowledge of polarity in molecules is going to help you understand intermolecular forces. First, let's make sure you understand the word intermolecular. Remember, a bond is the force holding the atoms together within the molecule. These forces are called intramolecular forces. An intermolecular force is the force holding the molecules together. Just like an interstate is a highway that goes between states, an intermolecular force is the force between molecules.
The forces of attraction between molecules are called intermolecular forces. The different types of intermolecular forces include dipole-dipole, hydrogen bonding, and London dispersion forces. These forces vary in strength but are all weaker than either covalent or ionic bonds. Intramolecular forces, the forces within the molecule, are always stronger than intermolecular forces, the forces between the molecules.
Let's talk first about dipole-dipole forces. These forces exist between polar molecules and are the strongest type of intermolecular force. What do we mean by the word dipole? A dipole is simply the result of a polar molecule with a partially positive end and a partially negative end. The prefix di means two, so in other words, a dipole has two poles. The force of attraction that occurs when the partially positive end of one molecule is attracted to the partially negative end of another molecule is called a dipole-dipole force.
The forces of attraction between polar molecules are called dipole-dipole forces. These forces result from the attraction between the positive end of one molecule and the negative end of another molecule. Dipole-dipole forces are the strongest form of intermolecular forces.
Now let's talk about hydrogen bonding, which is just a special type of dipole-dipole force. I bet you can even guess what special element is involved in hydrogen bonding.
Hydrogen!
You guys are so smart. When hydrogen is bonded to fluorine, oxygen, or nitrogen, it creates a particularly strong dipole. This is due to the fact that these three elements have very large electronegativities. This puts a larger positive charge on the hydrogen atom. When this positive charge comes in contact with an unshared pair of electrons on a neighboring molecule, a hydrogen bond is formed.
Hydrogen bonding occurs in molecules that contain bonds between hydrogen and fluorine, hydrogen and oxygen, or hydrogen and nitrogen. These bonds put a large positive charge on the hydrogen atoms, which creates an attraction for unshared pairs of electrons on neighboring molecules. This attraction between the hydrogen atom of one molecule and the unshared pair of electrons on the next is called a hydrogen bond.
Finally, all molecules experience a type of intermolecular force known as London dispersion forces. These forces result from the fact that electrons are constantly in motion. This constant motion means that the distribution of electrons at any given time in any atom or molecule can be uneven. This can create temporary dipoles that are weakly attracted to one another. These forces are present in all atoms and molecules, but they are the only type of intermolecular force in nonpolar molecules.
London dispersion forces, named after Fritz London, who discovered them in 1930, result from the constant motion of electrons in both atoms and molecules. These forces exist in all atoms and molecules and are the only type of intermolecular force in non-polar molecules.
And now it is time to use the force, the intermolecular force, to help you successfully complete your chemistry quiz.